continuing our conversation about permutations. Permutations are really about linear orders. So let's change that paradigm a little bit and let's consider in how many ways 4 spiders can sit at a circular table. Okay, and let's just do it again. Let's be concrete. So we can just put them around the table. This is one way that they could do it. And now, of course, I'm going to consider rotational symmetry here. So this is the same as if I just sort of rotate them all like this. How could I make a different arrangement? Well, I could take a different table and I could bring some more spiders along. And let's see, I want to make sure that I line it up so I can see that things are different. How about I do it like this? This is a different way that they're sitting. I can tell because these guys are the same, but look, these guys swapped positions. So let me see what else I can do. So I've got at least 2, right? They're 4 factorial permutations, so I know I'm not going to need more than 24 spiders, which is good because I don't have more than 24 spiders. Here's some more spiders. How else could we do this? Well, I could have it here. Ooh, let's put the red guy up there, and then maybe we'll put yellow and green. And now I'm going to do the same trick I did before of just permute the guys who are at the bottom. So these guys here and maybe these guys here. Okay. I got a couple more tables. I've got a few more spiders. Let's see what else we can do. We can put this spider here. We can put this spider here. We can put this spider here and this spider here. That's different. Haven't seen that one before. Now, how can I tell? How can I tell that what I'm doing right here with my spiders is actually giving me something different each time, and I haven't counted the same thing twice? Well, that's actually the crux of the argument. If you look, this blue spider, I've anchored him in the same position for each table. Now, by doing that, it helps me to see that, okay, these are all different, because if I just look after the blue spider, who comes up? And in fact, that's how we can answer this question. So the answer here is 6. Now 6 we've seen is a very common number. 6 is 4, choose 2, and it's also 3 factorial. In this case, it's actually 3 factorial. Why? Because I can think of, let one person be the head of the table. Linear order, line up the rest. March them in, let's say, clockwise from the head. That will give us a different linear order. So here, I've marched in yellow, green, red, yellow, red, green, red, yellow, green, red, green, yellow, green, red, yellow, green, yellow, red. So there I see the 3 factorial is coming. So in general, right, there's nothing special about 3. It's just 4 minus 1. So in general, if I want to say how many ways can I arrange n people at a table, it's n minus 1 factorial. That's going to be helpful in thinking about our next example. It's going to be a little less graphical. Now what we're talking about is cycle type. So when I talk about the cycle type of a permutation, what I mean is the partition that tells me the lengths of the cycles. So a permutation of 7 that has cycle type 3, 2, 2, let's just check 3 plus 2 plus 2 is 7. It is, so this makes sense. It means that I'm going to have my numbers in cycle notation be A, B, C, D, E, F, G. And I can ask myself, okay, given this structure, how many permutations of 7 have that given structure? Well, I can think here about what we just learned from this example. Here, I know that I could write this in a few different ways, right? So how many ways can I have a 3 cycle? Well, after I've chosen my 3 elements here, I have 3 choices for who's the head of the table. 3 choices for which letter begins this cycle, okay? And of course, for these guys, I'll have 2 choices and 2 choices as well. But then think about this. These are sort of 2 tables that have 2 people at them, right? 2 tables with 2 people. It doesn't matter which order these tables show up in, right? So here, I can permute the tables. I can permute all the tables that are the same size, and it doesn't really change what's happening. So if I put FG here and DE there, it's the same permutation. So there are 2 factorial ways to do this. So then in the end, if I think about all my information and gathering it up, what have I figured out? Well, if I think about the number of permutations of 7. That's 7 factorial, which is huge. I've definitely overcounted here. So what have I overcounted by? Well, there are 3 choices for the head of this table, and there are 2 choices for the head of that table, and 2 choices for the head of that table. So this is the table heads that I've overcounted by. But I've also overcounted by permuting the tables. So I've also got a 2 factorial hanging out in here. This is by permute the tables. So in the end, what I get is 7 factorial divided by 2 factorial times 2 times 2 times 3, which means that I have a total of 35. So there are 35 permutations of 7 that have this cycle type, and you can just check that that's really the case. But more interesting than this is writing down the general formula that we've just deduced, which is stated here in this theorem. So the formula is that the number of permutations of n with ai cycles of length I is given by this formula. Now again, I'll emphasize here, what are we doing? This is going to be permute tables of the same size. That's what we were doing over here. And now what are we doing here? This is choose the heads of all the tables. So this is what we're overcounting by. So we take the total number of permutations and divide out by what we're overcounting by when we're considering the cycle structure of a permutation. This is an important number in combinatorics that comes up all the time, and it's important to remember. We can check. Let's just do a sanity check real quick. And let's think about what happens when we only have one cycle, if we have just an n cycle. Well, that was the case that we did before. And we found that, okay, if we have 4 people, we got 3 factorial because we just counted with the spiders. Let's see how this formula shows us. Well, we'd have 4 factorial divided by, here we have ai cycles of length I. Well, we only have one cycle and it has length n. So I'm going to get here an is going to be 1. I'll get 1 factorial. That's for an because I have 1 n cycle. And then I have to choose the head, so I get n to the 1. The rest of these numbers are 0 factorials, which are 1, or number to the 0, which is also 1. So, sorry, n here is 4, but maybe we'll let it be n. So I get n factorial divided by n, which is n minus 1 factorial, which matches what we did just in that special case. So this formula generalizes the idea of the cycles. And this is an important one for you to remember about permutations.